Welcome to Catboy Gravity. So, we're going to be talking about the principle of equivalence and a little bit about special relativity. So, of course, recall that special relativity is, of course, general relativity in the limit where gravity does not exist. So, originally, we defined special relativity. So, special relativity. It is when so it's when all right, in general relativity originally we have g mu nu as our um our metric tensor, right? So it can be any tensor. It can be any tensor you want. Of course, we had the Schwarzschild. We practically spent the last few lectures discussing various candidates for the metric tensor. Of course, we had the Schwarz chilled metric tensor. We also had the Kerr tensor, the Kerr Newman tensor, and then we also had what else? We had the Reisner Nordstrom metric tensor. We also had, of course, the Alcubierre metric tensor, which uses the ADM formalism for general relativity. So Alcubierre. And then we had the Levi-Civita spacetime. So Levi-Civita, which deals with a cylindrically symmetric spacetime. And of course, we had a modification, so a change of coordinates in the Schwarzschild metric that gives us an Einstein-Rosen bridge, basically. So, right. Let's reframe what we know about special relativity. So we know special relativity is when we deal with things in flat space-time. So we'll say that special relativity is when, in general relativity, my metric tensor g mu nu is precisely my Minkowski metric. So eta mu nu. And you guys already know what the Minkowski metric is already. We've sort of discussed about this numerous times already. It's the matrix with zero everywhere except the diagonals, which is 1, 1, minus 1, 1, 1, 1. Or in as a line element, so if I multiply that with my covariant and contravariant vectors, so displacement vectors, I mean, dx mu, dx nu, which gives me my line element, it is basically minus dt squared plus dx squared plus dy squared plus dz squared. Now, I think when we do talk about quantum field theory in this series, when we get to that, I will switch the conventions a bit and flip the signs, but it really is just the same thing. We just change the signs. So, right, so this is my Minkowski metric, and you know that this is just an extension of the Pythagorean theorem to space-time. So there's that. So special relativity is when, in general relativity, my metric tensor is the Minkowski metric, and that's it in our reformulation. And all right, so now we've been going on about local reference frames. It's like, okay, so I have one reference frame over here, and I have another reference frame over here, and then we relate them via, or we at least relate their basis vectors. So stop falling. So when I have my basis vectors over here, so well, of course, we call it a E alpha, and then of course I have here a different set of basis vectors for this different Lorentz frame. So E beta, of course, the components of E alpha and E beta. So if I break this down into covariant form, we'll call it E alpha gamma, and then this is E beta, let's say E beta nu. So we relate each of these guys via a Lorentz transform. So this is basically E beta is equal to some Lorentz transform lambda, capital lambda E alpha. So, right, we've been talking about or going about and studying, especially when you guys studied general relativity, we've been studying about transforms between these local Lorentz frames. But then, don't you guys ever thought to yourself, what if we just consider the entirety of space-time, everything in it with our catboys and our femboys, we consider all of them as one single Lorentz frame? Now, there are some problems with that. So part of the problem that prevents us from constructing a global Lorentz frame comes from an earlier lecture. But before that, let's give yet another reformulation of what special relativity is. So this was given by Professor Scott Hughes, of course, in his lectures on general relativity, and I think it's a brilliant reformulation of what special relativity is. So another way of saying what special relativity is, special relativity is the theory that allows us to cover the entire space-time. So the entire space-time manifold. So because of course space-time is a manifold, we've gone over this multiple times already. The entire space-time manifold. So as to cover the entire space-time manifold with or using inertial reference frames. And of course, recall that an inertial reference frame is of course a set of clocks and measuring sticks. Well, loosely speaking, it's a construction by Thorne and it was a sketch by Blandford and Thorne. But yeah, this is our reformulation of what special relativity is. So now this does not imply that we can construct a global reference frame, but what we can do, of course, is to cover a manifold with these reference frames. So that's what our reformulation is, and I think it's a good one because of what we're gonna talk about next. So in a previous lecture, I talked about gravitational redshift. So essentially, just a little refresher, if you guys aren't still fresh or if you guys have sort of forgotten about it, if I have a gravitational field here. So let me just try to draw this properly. So like this. I suck at drawing these things. So this is my gravitational field, essentially, or my well in space. So if I shoot a photon through this gravitational field, of course it's going to be induced by mass. So this bending of space-time, albeit a very inaccurate portrayal of bending in space-time. I'm going to get a circle here. All right, this is better. So, all right. So I have a mass over there that bends my space-time. If I shoot a photon, I'm going to use green for this because it looks cool. If I shoot a photon through the system, of course, its trajectory is going to be bent because of the curvature of space-time, albeit even though according to its reference frame, it's traveling in a straight line, to us it looks curved. That's essentially that's a very loose analogy of what the principle of equivalence is. So right? It passes through the space-time, and then because it passes through the space-time and it experiences some gravitational attraction to that body, it essentially loses some energy to that body, or because of that gravitational attraction, and then it shifts. Because it loses energy or gains energy, the photon changes wavelengths. Because of course, using the de Broglie relations, we of course recall that we can associate the mass. I mean, not only the de Broglie relations, but really the energy equivalence. So the original E squared equals m squared c to the fourth minus p squared c squared. Right. So, I mean, if we set this p equals to 0 and then take the square root of both sides, we get the original energy equivalence, E equals mc squared. And using this, of course, we can associate the mass of the particle, right, and its energy. And when it loses energy, using the de Broglie relations, you can conclude that it changes wavelengths, because the de Broglie relations relate the wavelength to the energy of my particle. And so, right, it shifts frequency, not frequency, I mean wavelengths, and changes color. That's why we call it redshift. So that was a quick overview of what gravitational redshift is. But let's make this more precise, but not precise at the same time. All right, let's do an experiment that Scott Hughes did. But let's reformulate it so that it's more appealing to you guys. So consider me on top of a building. So here we go again with, you guys can probably see where this is going. Let's see how, let's see if I can draw a building properly. All right. Okay, so this is the ground, and then let's say this is of height h, and let's say I'm standing on top of the building. All right, so I'm on top of the building, and let's say I drop a catboy off this building, right? So I push him off the edge. Yes, we're continuing with our torture of catboys, and just so you guys know, it's for the sake of science. So I have my catboy, and then he's falling. And then let's say at the bottom, at the ground, there is a machine. So we're not quite gonna kill, or right, we're not gonna delete this catboy from existence, but rather, right, he's gonna be saved by a machine at the bottom. Let's call this machine a photonulator. It's a funny term that I think is pretty fitting. So let's call it a photonulator. So from the wacky inventions of Dr. Doofenshmirtz, we pulled this wacky one out for the purposes of this experiment. So it's a photonulator. We call it a photonulator because it converts that catboy into a photon, a singular photon. So as soon as the catboy falls, the photonulator is gonna immediately stop him from dying and convert everything in his being into a photon. And of course, conservation of energy still holds. Don't worry. To the engineering department of LOSC, there's nothing hellish about this contraption. It's still gonna conserve energy, whether it be dissipating it to the environment or something like that, like say sound or a fireball or something. So every bit of energy is conserved, just so you guys know. So the energy at the bottom, I'll call EB, is given by the mass of my catboy. So my catboy has a certain mass m. So m. So this is m plus mgh. Just so you know, this is a formulation of my potential energy, which involves the height h over here, the gravitational constant g. So there's actually local gravitational constant. So I'm calling this the local gravitational constant, just 9.8 meters per second squared. And yeah. So just so you guys don't confuse it with the metric tensor, basically. And then this is my height from the ground. And of course, m is the mass. So you guys can sort of rewrite this as m and 1 plus gh. So, As soon as my catboy gets converted into a photon, you'll notice, of course, that we'll have to express the energy in terms of quantum mechanics. So quantizing the system, because we're now dealing with a photon and not a catboy, we have to deal with its wavelength. So remember that the energy by the de Broglie relations, so the energy of a photon, so energy of a photon is h bar, so the reduced Planck's constant, times the frequency, or the frequency. So the energy of the photon at the bottom, so EB of the photon, which is our catboy converted by the photoniulator, that's precisely, of course, h bar omega b, where omega b is the wavelength at the bottom. And of course, that'll be equal to m times 1 plus gh, of course. So next, what I want to suppose is that there is another device at the bottom. I'll call it a recatboylator. So my recatulator. So the recatulator, what it does is, after the catboy gets converted into a photon, it reconverts that photon back into my catboy good as new. And of course, again, conserving energy, to maintain the appearance or the original look of the catboy so that he's good as new. Maybe he's going to draw energy from the environment or something like that. So in all of this, energy is conserved. So there is no extra factors we have to consider when we're talking about, of course, the energies. So once it reconverts my catboy, of course, it's going to shoot back up. So when given all this information, then what I want to find out then is, what is the energy at the top? So what is ET? So of course, going back to my de Broglie relation, ET is equal to h bar omega t, where of course omega t is the wavelength up there. But the thing is, all right, so when I drop this guy, when I drop this catboy, it gets converted into a photon, and then the re-raculator or the recatulator reconverts them back into a catboy. What I can do essentially is just keep doing this process of dropping him and then sort of converting them into a photon. And then when I keep doing that, right, there's going to be energy that gets spread out because we have to conserve energy to convert them back into a catboy or convert them into a photon. And but the thing is, if I keep repeating this process and I keep raising him up and then dropping him and then converting all that energy, what I essentially get is a perpetual motion machine. So what we've essentially done with this experiment is we have broken the laws of physics. What now? So what I want to do instead is I'll say that the energy at the top, so ET, is equal to mass. So what then? We can say then that the energy at the top divided by the energy at the bottom, so this ratio, is equal to the mass over mass times 1 plus GH. And then that is equal to the wavelength at the top divided by the wavelength at the bottom, times some extra factor GH. Let's put in a c squared, but of course we keep in mind that c is equal to 1. So then we can say that the wavelength at the top is equal to the wavelength at the bottom times 1 plus GH. And then, of course, from there we can conclude that ET, so energy at the top, is h bar times the wavelength at the bottom times 1 plus GH. So this is the energy of the photon at the top. So if we don't reconvert them and then shoot them upwards, this is what the energy should be at the top. Okay. So this experiment is actually verified, albeit in a less silly manner. It's verified by the Pound-Rebka experiment. So uh, Pound-Rebka. So Pound and Rebka um, verified this observation and this principle. So this is like a sort of our way of talking about redshift. So it changes energy in the end of the day. So the energy at the top and the energy at the bottom will essentially never be the same, right? So, of course, we have G, our gravitational constant, and then we try to make him climb out of the gravity well. The energy is not going to be the same. So that's just what I was trying to say with all this. So that sort of prevents our goal of trying to construct a global inertial reference frame, so to speak, a global with quotation marks, because things essentially change. The relative inertia, when I try to measure its energy in this certain reference frame, if I'm in a global Lorentz frame, it should be invariant. Energy should be invariant. If I shift this one, or if I shift this inertial reference frame to a higher vantage point in this global reference frame with respect to the ground of a body, a celestial body with enough gravity to affect that object's, trajectory, it should essentially have the same energy, but it does not have the same energy because it depends on the gravitational attraction. And of course, there will be a shift in the energy of that object as I raise it. It will increase, or its potential energy will increase, right? And as I drop it, it's going to convert all that into kinetic energy. And it will have more kinetic energy converted from the potential energy as if more than if I had just dropped it from a lower vantage point with respect to the ground of that planet or that gravitational object, or the object that generates a gravitational field. So that experiment by the Pound-Rebka experiment essentially verified that light gets redder as it escapes a gravity well. Now another skewed but somewhat similar in the sense we're in, of course, light bends in space-time, is gravitational lensing. So suppose I have my Schwarzschild metric. So suppose I have my G mu nu, and then that is the diagonal, of course, of 1 minus Rs over R. That's minus. And then this is 1 minus Rs over R to the minus 1. That's R squared sine squared theta. So this is my Schwarzschild metric. And we know from way back then, that this is only valid for R greater than, or strictly greater than Rs. So let's say that R is strictly less than Rs. So then we have a black hole. So I have a black hole over here. So a catboy, that's a black hole. Essentially a dead catboy. So there will be a ring of matter around this. So if my singularity is over here, there's going to be another region of space-time called the horizon, which is also black, because as soon as you cross that horizon, you cannot get out. Your world line will essentially only point inwards. And even the world lines of any light cone will be bent towards the singularity. So you cannot not even light can escape it. And if light can't escape it, what chance do you have of escaping that black hole? So, all right. So let's say I put a camera over here, an observer. So let's say I'm over here. And then I shoot a bunch of photons. So it's essentially going to get bent. So, and then my eyes receive it. All right. So that gravitational lensing is the cause of why in some renders of black holes you see on the internet, like artistic expressions, you see sort of there's like a warping of space around the black hole. So say this is my black hole. And then there's like some weird fuzzy like warping of objects around it. And you see like it's spinning. Let's say on a Kerr black hole or Kerr catboy, you'll see that it's it's like there's like matter spinning around the horizon. Yeah, that's the cause of gravitational lensing, and photons getting like, light getting bent as it travels from the back of the black hole towards your eyes. All right. And that can also be seen in the first ever black hole that we took a picture back in 2018, or I think much later. You guys can see like sort of white and yellowish stuff around the black hole itself. And that's an effect of gravitational lensing as well. Alright, so let's get to part 2 of my argument on why we cannot construct a global reference frame. So going back to the original question at the beginning of the video, we originally asked ourselves, if we keep talking about local Lorentz frames, what if I want to just construct a global Lorentz frame and then just sort of do physics from there? And of course, my answer is no. And this video is me sort of justifying that as a prelude to when we discuss about the equivalence principle. So now, suppose we could cover a large region of space-time with a single Lorentz frame. So let's assume the contrary for my second part of the argument of why we can't construct a global reference frame. So we're gonna use a proof by contradiction. This isn't a proof, it's just a sketch of an argument, but it should give you guys a good intuition as to why we just can't do it. So suppose we could, suppose we can construct a global, in quotation marks, because we still have not defined the notion of global and local. So construct a global Lorentz frame. So Lorentz frame. So suppose we can do that. So now what I want to consider next is a wave. I want to consider next a wave. It can be any disturbance. It can be a gravitational wave. It can be a electromagnetic wave. Let's consider an electromagnetic wave. But the gist is it's a wave, a disturbance through space-time. So let's consider the world line of successive crests of a wave. So what I'm talking about is these guys over here, the crests of that wave, and we want to consider how they move through space-time. All right, so if we can cover, all right, so here's how the argument goes. If we can cover space-time with one Lorentz frame, space-time is translation invariant. All right. So to illustrate this, I'm gonna use a space-time diagram. So this is my time, and then this is my x direction. So I mean my z direction. So it looks a bit skewered, but you guys will see in a moment why I picked this orientation. So let's call this line the bottom, and then this is the top. So this is my throw, and this is my crest. So this is my bottom, and then this is my top. So the crests will look something like this. All right. So this is how they travel through space-time, essentially. Now, if we can cover space-time with one Lorentz frame, space-time is translation invariant. What do I mean by that? What I mean by that is essentially if I move my crest through space-time, it would have to be the same as some other sort of thing here. So if I make another crest, or if I try to do another crest over here, it must be the same. These have to be congruent. So if I denote this over here, so let's add some formalism here. So let's call this over here delta t, delta time top. And then let's call this over here, I'll use yellow, delta time bottom, so B. So it must be the case that these changes are the same because again we're translation invariant. So it must be the case that because we can construct this global reference frame, we can translate these crests seamlessly. So TB must be equal to delta T T. So that must be the case because it's translation invariant. But the thing is, my delta time, delta T T, is essentially 2 pi over the wavelength, physics 101, which also must be delta TB. I mean, because this is the case, because it is 2 pi over the wavelength, it must be the case, it must be that this delta TT is not the same as delta TB. Again, if I try to shift these guys together, right, they have to be congruent. So that means that this expression 2 pi over the wavelength essentially has to agree on both of these guys. But it's obvious that the wavelength of one crest is different from the wavelength of the other crest. So of course this is crest 1, this is crest 2. Their wavelengths must be different because these guys are modulating at a different time, right? But the thing is, if I try to equate these things, if I try to make this expression agree on both terms, that would mean that these guys are essentially at the same slice of time in my space-time diagram. But they're not. These are two different crests, and they are positioned at different positions in my space-time. So that means they can't have the same change in time as they propagate. But because we claimed at the beginning that we could have a global Lorentz frame, it's translation invariant. So that means they have to be the same, but they can't. We just showed that they can't. So there's a contradiction here. So it must be that we really cannot construct a global Lorentz frame. And this argument, so this argument I presented just now was presented by Alfred Schild. Or Child. I don't know if he was one of the contributors to the Schwarzschild metric, but it's cool. So, all right, so that's pretty sad. We can't do all of physics in one single neat local global Lorentz frame, but we still have our local Lorentz frame. So there's at least some recourse that we can to these things. So while we can't have global Lorentz frames, we still have our local Lorentz frames. All right. So in the next argument that I'm going to do, or next thing that I'm going to show you guys, which is frankly an amazing primer on principle of equivalence, what I want to do is I'm going to call Lorentz frame. So I'm going to say that Lorentz frame is equivalent to inertial inertial frame. Yeah, inertial rest frame. Inertial frame. Okay. And then what I want to now consider is something called a freely falling frame. So freely falling frame. And what I mean by freely falling frame is that it is an inertial frame or Lorentz frame that is not subject to any forces. So it's not subjected to like wind or air resistance. It's only subjected to one singular force. And I mean, not really force, but one singular thing, and that's gravity. So that's what I mean by freely falling frame. So it experiences zero relative acceleration in observance of other forces. So that's what I mean by that. So within this frame, this FFF, objects maintain relative velocities. So essentially, but the thing is, tides break down the notion of uniform, freely falling frames. So to illustrate that argument, let's consider a very tall elevator. And then I put 3 catboys inside it. Again, with torturing the catboys, but it's in the name of science. So I have one over here, and I have one in the middle, and I have one at the bottom. And let's say there is some gravitational force, or some gravitational force over here. So, um, all right, so whenever we're dealing with things that travel through space-time, when we sit still, or let's say I have a bottle of water and then I let it sit still on a table. Although it's not moving with respect to what we're seeing or with respect to the table and the earth, it's still moving with respect to time. As it goes through space-time, or as time ticks forward, it is moving through space-time. All right, you guys get the idea? It's essentially just still traveling. It's still moving with respect to time. All right, so of course, how it moves through time is dependent on how we want to define what time is. With respect to it. So, essentially, what I'm saying is that if I try to construct a space-time diagram of these 3 guys, it would look something that looks like this. So, this is my height z. So the height of each of these guys are gonna be z essentially. Oh. All right, z. And then this is my time. You notice that one of these guys will travel straight through time. So it's essentially this guy over here. He's gonna keep traveling through space-time like this. Now this guy is gonna be subjected downwards. I'm gonna use green for that. So this guy's gonna will have like some potential going downwards. And then because this guy is way high up in space, he'll essentially have no gravity influencing him. So he's essentially gonna veer off into space. So this is what my space-time diagram will look like. So essentially these guys are non-parallel. But So what I'm really talking about is their reference frame. All right, so this wrong color. This reference frame, and then this reference frame, and then this reference frame that contains them. All right. So this is a space-time diagram of their reference frames. So in a normal flat space-time, you guys know that these guys are just gonna keep going on. They're just gonna keep going through time. They're essentially not going to be traveling through space-time. So this is what happens when I leave an object on a piece of table. In the off chance that it should have been, so when it should have been falling to the ground according to gravity, it's being held up by a opposite force, which is the table itself. So the table gives an upward force that balances out with the gravity. So essentially no gravity right now, and it's flat. It stays through space-time. But as soon as I remove the table, you notice it start to drop. And I illustrated this in the last lecture, wherein I have something that's falling, and then we only see sort of slices of its motion through space-time. So this is time, and then this is my height, and we only see slices of this guy's movement, and each of these slices show that the object is falling linearly, but through space-time it's moving in a curved sort of world line. So that's essentially my principle of equivalence. So the principle of equivalence essentially states the following. So principle of Equivalence. And then again, the definition was taken from Professor Scott Hughes' lecture. So over sufficiently small regions, the motion of freely falling particles of freely falling particles due to gravity cannot be distinguished from uniform acceleration.
You done?
No. So, the principle of equivalence essentially states that over sufficiently small regions, the motion of freely falling particles due to gravity cannot be distinguished from uniform acceleration. So, going back to classical mechanics from physics, we know that uniform acceleration is essentially like an object that's constantly accelerating. It's not being changed by any external factor. So essentially, it's a generalization of gravity. So general force or term for gravity. So what I'm essentially saying is this over here. What the principle of equivalence is saying. Well, this is actually the weak equivalence principle. Weak equivalence principle. This is what it was essentially saying. That this curved motion of objects falling towards, say, a celestial catboy under gravity or because of the gravitational field is not because of some force that pulls them towards the object or that astronomical catboy, but rather it is because of the intrinsic curvature of space-time induced by the mass of that catboy that causes its world line to travel in a seemingly curved trajectory. So what we perceive as an object falling towards the surface of a catboy in a straight line is essentially it moving through space-time in a curved trajectory. So that's the principle of equivalence, at least the weak form. There are other forms of this. Of course, there's the strong equivalence principle, which states that gravity falls in the gravitational field in a way indistinguishable from mass. But that's something else. And we can also reformulate it by saying, in sufficiently small regions of space-time, we can find a representation such that the laws of physics reduce to those of special relativity. So, what I mean by that one, which is called the Einstein equivalence principle, is that essentially, right, so overall, if we look at the sphere, globally speaking, well, quote unquote, globally speaking, it's a sphere, it's curved, right? But the thing is, when I defined what a manifold was, recall that when I defined it, it's a local topological space. So, I mean, a topological space that's locally Rn. And Rn is flat, no doubt. No matter which way you put it, Rn is flat. Even though you convert it to polar coordinates, it may look curved, but it's actually just a reformulation of flat space-time. Nothing is bent, there's nothing else there. So essentially, Rn is an example of a Minkowskian space-time, or Minkowskian space-time. So what I'm essentially saying with this equivalence principle, the Einstein equivalence principle, and it's a general rule of thumb for people like you and I when we're studying general relativity, that anything with Einstein attached to its name is important. So the Einstein equivalence principle. So the Einstein equivalence principle basically tells me that it basically reformulates our notion of our primary definition of a manifold in terms of general relativity, essentially. So while globally we're considering or away from the space or away from that object, we're considering curved spacetime. On the surface of that object, we are considering Minkowskian spacetime, or Minkowskian spacetime, essentially. So, in a sufficiently small region of spacetime, again, I'll grab the circle. So, in a sufficiently small patch of the circle, let's see over here. So in this little patch of my sphere, it should reduce to Minkowskian space. While the space around my mass should be something that's not Minkowskian. So G mu nu is not eta mu nu. While locally speaking, G mu nu is eta mu nu. And essentially, for that sufficiently small region on that object, while around it, it's not, it's not special, it's not Minkowskian. On the surface, it must be Minkowskian. It must reduce to special relativity. And that'll be it for this lecture. So, not sure what we're going to discuss next lecture. I think we're just going to be discussing more spacetimes. So that'll be it for this one.